Okay, picture this. You're a shepherd, maybe around 800 BC, out in Magnesia, Asia Minor. Suddenly, your sandals feel stuck
Stuck to what?
to a rock, a weird, dark rock. The iron bits on your staff, the nails in your shoes, they're all being pulled towards it.
Wow.
Yeah. And believe it or not, that sort of weird moment is where a deep dive starts today. We're diving into magnets.
It's amazing, isn't it, how something like, well, a shepherd tripping over a magnetic rock, basically,
Yeah.
kicks off this whole field of science. That rock, lodestone, was the first natural magnet anyone really noticed.
Exactly. So that's our plan for this deep dive. Unpack magnets. You know, from that ancient find right up to how they, power everything today.
All right.
Our mission is pretty straightforward. Pull out the really important stuff about natural magnets, the ones we make, that invisible force they have, and why they always seem to point north.
Yeah, that persistent pointing.
We've got some solid educational material here, so the idea is you'll get the basics, the aha moments without drowning in jargon.
And it's worth remembering that Shepard's story isn't just a fun fact. Understanding magnets, it's fundamental to so much tech we use every single day.
Absolutely. So let's start right there. What is a magnet, fundamentally?
Good question. Okay, so at its heart, a magnet is an object, usually made of something like iron.
Okay.
And it creates this invisible area of influence around itself, a magnetic field.
Right, the field.
And that field pulls on other things made of iron. That pull, that's magnetic attraction. The force doing the pulling is the magnetic force. Simple as that, really.
Got it. And it's important to know what responds to that force, right? Because not everything does.
Exactly. Our sources make a clear distinction. You've got magnetic substances, sometimes called ferromagnetic substances. Think iron, steel, cobalt, nickel.
Like your fridge magnet sticking to the steel door?
Perfect example.
Yeah.
But then there's a whole bunch of stuff that magnets just ignore.
Like wood, plastic, copper.
Paper, aluminum, rubber, stone, sand, ceramics, glass.
Even gold and silver.
Yep. Gold, silver, brass, totally non-magnetic. You could put a super strong magnet next to your wooden table, nothing happens.
Right. Okay, so back to that first rock, the lodestone, magnetite. What's special about those natural ones?
Well, the really neat thing is they're just found that way, already magnetized, like Magnus's rock.
Just lying around, being magnetic.
Pretty much. And the name lodestone itself kind of gives it away. It means stone that leads or indicates direction. People noticed early on they'd line up north-south.
Ah, the direction finding. And magnet comes from Magnesia, where they found a lot of it.
Exactly. That geographical connection is key. And then, of course, we figured out how to make our own artificial magnets.
Right, the ones we manufacture. What's different about those?
Well, we usually make them from steel, and we can shape them however we need. You know, the classic bar magnet.
Or a horseshoe shape.
Yeah, the horseshoe magnets are great for concentrating the force.
Yeah.
But you also get U-shapes, cylinders, and really importantly, the little magnetic needle in a compass.
Our sources actually show a bunch of these shapes. Bars, horseshoes, U-shapes, cylinders, those compass needles, each shape has its use.
And no matter the shape, they all share this core feature. They have poles. Magnetic poles.
Okay, poles. Tell me about those.
So if you hang a magnet, like a bar magnet, so it can swing freely,
Yeah.
it won't just spin randomly,
Yeah.
it'll always settle down pointing roughly north and south, geographically speaking.
Okay.
The end pointing north,
Yes.
that's the north pole, sometimes called the north-seeking pole.
And the other end is the south pole, the south-seeking one.
You got it. And here's the kicker. Every single magnet, whatever its shape, always has both, a north and a south pole.
Always both. You can't just have a north.
Nope, we'll get to that. But first, where's the pull strongest on these magnets?
Ah, yeah, that's easy to see. If you take a magnet and dip it in iron filings,
Right.
all the filings cluster right at the ends, at the poles. Hardly any stick to the middle part.
That's a great visual. It shows perfectly that the magnetic strength is concentrated right there at the poles.
So what happens if you try to, separate them? Break a magnet in half. Do you get a north piece and a south piece?
That's what you'd think. Right. But nope. It's fascinating. If you snap a magnet, say a bar magnet, in two,
Yeah.
each piece instantly becomes a new complete magnet with its own north and south pole.
Seriously, so you just get two smaller magnets.
Exactly. You can keep breaking them, and you just keep getting smaller and smaller magnets, but
Yeah.
each one always has a north and a south pole. It's like a fundamental rule.
Wow. Okay, so you can never isolate a single pole. They're always paired up.
Always in pairs. That's a really core idea. So now we know they have poles. How do these poles interact?
Ah, the classic rule. Like poles repel, unlike poles attract.
Give me an example.
Okay, Bring the north pole of one magnet near the north pole of another. You feel them push apart, repel.
Okay.
Same thing if you bring two south poles together, push away.
Right.
Bring a north pole near a south pole. Snap. They pull together strongly. Attract. It's like opposite personalities attracting.
A fundamental push and pull. Now, our source points out something important about testing if something is a magnet. Why is repulsion the only surefire test?
Yeah, this is a smart point. See, a magnet will attract any old magnetic thing, like a plain steel paperclip. That's just attraction.
Okay.
So if two things pull together, one might be a magnet and the other just a piece of iron. You don't know for sure if both are magnets.
Ah, right.
But if two objects push each other away,
Repel.
then you know absolutely that both are magnets. You're seeing two, like, poles, two norths or two souths, facing each other. That repulsion is the giveaway.
That's the definitive proof.
Interesting. Okay, so we've talked natural versus artificial. The source also splits magnets another way based on how long they stay magnetic. Temporary versus permanent.
Right. Temporary magnets. They're like magnetic sprinters. They only work for a short time.
Okay.
They're usually made of soft iron, pure iron. And they're only magnetic while they're near a strong magnet or in a strong magnetic field. Take that field away.
Pretty much. The magnetism disappears almost completely. Think of paper clips clinging to a magnet, but then falling off when you remove the magnet.
And they're not very powerful themselves, right? These temporary ones.
No, generally weaker. They can't easily magnetize other stuff on their own.
Gotcha. So what about the other kind? Permanent magnets.
Ah, these are the marathon runners. They're made of materials like steel, sometimes cobalt or nickel. And the key thing is they hold on to their magnetism for a long, long time.
Even after whatever magnetized them is gone.
Exactly. They stay magnetic. And they're usually much stronger than temporary magnets, strong enough to even temporarily magnetize other iron things nearby.
So the material makes the difference. Soft iron for temporary, steel for permanent.
Precisely. Our source calls them soft magnetic materials and permanent magnetic materials. It's about how easily they magnetize and, crucially, demagnetize.
That makes sense. It's about how well the material remembers its magnetic alignment. Okay, then there's a third really interesting type, electromagnets.
Yes, electromagnets. This is where electricity and magnetism team up. It started back in 1819, Hans Christian Ørsted.
The Danish physicist, what did he find?
He noticed that if you have an electric current flowing through a wire, it creates a magnetic field around the wire.
Just the current itself?
Yeah, a moving electric charge creates magnetism. That discovery was huge. It led straight to electromagnets.
So how do you make one?
You take some insulated wire, coil it up, usually around a core of soft iron.
Soft iron, like in temporary magnets?
Exactly, good catch. You use soft iron because you want it to become magnetic only when the electricity is flowing. Pass a current through that coil.
And the iron core becomes a magnet.
Bingo. A temporary magnet, but potentially a very strong one. Our source has diagrams showing this. A coil around an iron bar or horseshoe shape.
So the big deal here is control, right? You can switch it on and off.
Precisely. Turn the current on, you have a magnet. Turn it off. The magnetism basically vanishes. That's a massive advantage over permanent magnets.
I can see that. What are the other advantages?
Well, besides the on-off switch, you can make them incredibly strong. Much stronger than many permanent magnets.
Now, more power.
Yep. Increase the electric current flowing through the coil, or just wrap more turns of wire around the core. Both make the magnet stronger.
More current, more turns, more magnetism.
Right. And here's another cool trick. You can flip the poles, reverse the direction the electric current flows.
And north becomes south, south becomes north.
Instantly. You definitely can't do that with a bar magnet you bought at the store.
No, definitely not. That level of control is amazing.
Huh.
Okay, so we know about the types. How do we actually make magnets? We touched on electromagnets, but what about other ways?
Right. One simple way is called magnetic induction. Remember how a magnet attracts a paperclip?
Yeah.
Well, if you bring a strong magnet near an iron nail, say,
Yeah.
without actually touching it,
Uh-huh.
that nail itself becomes temporarily magnetic. It's induced. It might even be able to pick up tiny tacks or something.
But only while the main magnet is nearby.
Exactly. Move the permanent magnet away, the nail loses its induced magnetism almost immediately. It's like the magnet's field temporarily lines things up inside the nail.
Induction, got it.
Yeah.
What about making more lasting magnets?
For that, we have the touch methods. There's the single touch method. You take one pole of a strong magnet, say the North Pole,
Okay.
and you stroke it along an unmagnetized iron bar, always in the same direction, lifting it away at the end and starting again. Repeat that maybe 20, 30 times.
And the bar becomes magnetic?
It gets magnetized, yeah. It picks up some permanent magnetism.
Okay, single touch. What else?
There's also the double touch method. This uses two strong magnets.
Two. How does that work?
You put the iron bar down, you place the opposite poles of the two magnets together in the middle of the bar, like north and south touching.
Right, in the middle.
Then you drag them apart simultaneously, stroking towards opposite ends of the bar. Lift them off, bring them back to the middle, and repeat.
Sounds a bit more complicated.
Maybe slightly, but it's another way to do it. And of course, the third method is the electrical one we already discussed, making an electromagnet.
Right, wrapping a coil around iron and running a current through it. Probably the most effective for strong magnets.
Generally, yes. Especially for controlled magnetism.
Okay, so we can make them?
Yeah.
What about destroying the magnetism? How do you demagnetize something?
Turns out there are quite a few ways to mess up a magnet's mojo.
Like what? Dropping it?
Dropping it repeatedly, yeah, especially onto a hard surface. Rough handling in general isn't good for them. Hammering it can work too.
Physical shock, basically.
Exactly. Heat is another big one. If you heat a magnet up really hot,
It loses its magnetism.
like it can, yeah. Especially if you let it cool down while it's pointing east-west instead of north-south, that
Yeah.
seems to help scramble its internal alignment.
Interesting. East-west. Any other ways?
You can use electricity again, but this time alternating current, AC. Pass AC through a coil around the magnet, then slowly withdraw the magnet from the coil, and finally just leaving a magnet lying around improperly.
Improperly. Yeah, without keepers, we'll get to those. If the poles are just left open, it can slowly weaken over time. That's called self-demagnetization.
So basically, anything that physically shakes up or thermally scrambles the internal magnetic order or messes with it using AC fields can demagnetize it.
Pretty much sums it up. So maybe we should quickly recap the key properties of, say, a typical bar magnet, just to lock it in.
Good idea. Go for it.
Okay, first, the attractive property. It pulls on iron, steel, stuff like that. Think iron filings.
Check.
Second, the directive property. Hang it freely, it points north-south. That's the compass principle.
Check.
Third, the interaction rule. Likes repel, unlikes attract. North repels north, north attracts south.
Got it.
And fourth, the big one we discussed.
Yeah.
Poles always exist in pairs. Always a north and a south together, never just one.
Excellent recap. So if these magnets can lose their strength, especially permanent ones over time, how do we store them properly to keep them strong? You mentioned keepers. Right, magnetic keepers. These are super important for preserving permanent magnets. They're usually just pieces of soft iron.
Soft iron again. Why soft iron?
Because it provides an easy path for the magnetic field lines to travel outside the magnet, from one pole to the other. It essentially completes the magnetic circuit.
Ah, okay. How do you use them?
Well, for bar magnets, you typically store them in pairs, place them side by side with opposite poles next to each other, north next to south, south next to north.
Okay, pairs with opposite poles adjacent.
Yeah, maybe with a little wooden spacer between them. Then you place a soft iron keeper across the ends, connecting the north pole of one magnet to the south pole of the other at both ends.
So the keepers bridge the gap between opposite poles?
Exactly. It gives the magnetic field a nice closed loop to flow through, which helps keep the magnet's internal domains aligned and strong.
Makes sense. What about like a horseshoe magnet?
Simpler. Just one soft iron keeper placed straight across the two poles. Same principle. Completes the circuit, protects the magnetism. Right, provides that closed loop. Okay, this is all fascinating stuff, but let's get to the really practical side. Where do we actually use all these magnets?
Oh, everywhere. I mean, the list is huge. Start with the obvious, the magnetic compass. Essential for navigation for centuries, travelers, sailors.
Still used today, even with GPS.
Absolutely. But think smaller scale, too. Doorbells often use electromagnets. The seal on your refrigerator door. Magnetic strip.
Cupboard doors, too, sometimes, those little magnetic catches.
Yep. Then you get into more complex machines. Dynamos generating electricity, electric motors making things move. Magnets are crucial core components.
What about sound and data?
Big time. Loudspeakers and microphones rely on the interaction between magnets and electric currents to work. Older storage media, like floppy disks and magnetic tapes, use magnetism to store data.
Wow, floppy disks, blast from the past.
Right. Stereo speakers, older TVs.
Yeah.
Even modern computers use ceramic magnets in various places.
And toys. Lots of toys use magnets for cool effects.
Definitely. And then there are the heavy-duty applications. Giant electromagnets lifting tons of scrap metal in junkyards or cargo in ports.
Those are impressive.
And delicate uses, too. In science labs, electrical measuring instruments like galvanometers, ammeters, voltmeters often use magnetic principles.
You mentioned medical uses, too.
Yeah, eye specialists sometimes use carefully controlled, small electromagnets to remove tiny bits of iron or steel if they get lodged in someone's eye.
That's incredible. From lifting cars to removing tiny specks from an eye.
It's a huge range. And maybe the biggest magnet of all, Earth itself. It behaves like a giant, though complex magnet, giving us our magnetic north and south.
Even without a literal giant bar magnet inside.
Exactly. It's generated by flows in the Earth's core.
Yeah.
But the effect is there. It really shows how fundamental magnetism is.
Okay, so wrapping up this deep dive, wow, we covered a lot. From that possibly legendary shepherd
Magnus and his sticky sandals.
to the basic rules, attract, repel. We looked at temporary magnets that forget quickly, permanent ones that hold on, and those super useful electromagnets we can control.
And the key takeaway, always worth repeating. Poles always, always come in pairs. North and south, forever together.
Absolutely. So here's a final thought to leave you with. Mull this over. If we could somehow, get really precise control over the Earth's entire magnetic field.
Control the whole planet's field.
Yeah. What could we do with that? Think beyond just better compasses. Could it change communication? Could we, boost our protection from solar winds?
That's a big what if.
And maybe that old story about Magnus. Maybe it wasn't just a story about discovering a weird rock. Maybe it hints at some deeper connection, something we're still figuring out, between us and this invisible magnetic force all around us. What do you think?